All right, let's get started. Welcome to the monthly Affinity Group meeting of the University of Hawaii AI Precision Health Institute, where we do a lot of AI for biomedicine. And today we have a very special guest from Northwestern. I'll introduce Professor Luo in a second. But first, I just want to bring everyone's attention to the upcoming speakers we have. Every month, we invite a speaker, and we have a very good lineup in the next couple of months. You can sign up for the email list at our website, ifi-shepherdresearchlab.org. The purpose of this affinity group is to bring together a bunch of diverse researchers to focus on AI for biomedicine. So we bring together students, trainees, faculty, researchers in computer science, engineering, nutrition, epidemiology, radiology, clinicians, and advocates. The focus is on discussing trends and applications of AI in cancer research and clinical practice. The goal is to foster collaborations, and we're very excited to have people from all over the world joining us on these meetings. Students, trainees, and faculty with no background in AI are encouraged to attend, but also people who are actively working on this in this area. Please send feedback and suggestions to Dr. John Shepard and Peter Washington, who are faculty here at UH. And as compensation for our wonderful speakers, we are going to send our speaker today a beer stein that has the AI Precision Health logo on it. And some of our past speakers have sent us photos of them enjoying beer from their steins. So today, we're very lucky to have Professor Yuan Luo. He's an associate professor at the Department of Preventative Medicine at Northwestern University's Feinberg School of Medicine. He's also the chief AI officer at the Clinical and Translational Sciences Institute and the Institute for AI in Medicine. Professor Luo is a fellow of the International Academy of Health Sciences Informatics and a fellow of the American College of Medical Informatics, also a fellow of the American Medical Informatics Association, and his views have been featured in The Economist, JAMA Network, and the Becker's Hospital Review. So we're very pleased to have him, and we're excited to hear what he has to say today.
Thank you for the great introduction, and it's a great pleasure for me to be here. First, let me share the slides. So can people see it fine?
Yes, we can see it.
Okay, great. So today I'm going to talk about large language models for biomedical research. And first, let's take a look at what some of the large language models may be. In the field of NLP, perhaps the most significant development recently is the large language models. And there are two representative architectures. One of them is BERT and the other is GPT. While GPT only considers the left context when making predictions, BERT, on the other hand, takes into account both left and right context. So as illustrated in this figure here. In addition to the architecture differences, the earlier model of the LLMs, such as Elmo, is feature-based approach, but BERT and GPT, they are fine-tuning approaches, and so will be our focus at this talk. So this is a diagram illustrate the three steps of the ChatGPT, and it's an early version that's published under the name of InstructGPT, but I think under the core, the technique is very similar, if not the same. So the three steps, the first one is supervised fine-tuning, and the second one is reward model training, and the third one is reinforcement learning via proximal policy optimization. And as you can see, this is basically a human-in-the-loop approach because the second step of the reward model training is actually training the model to mimic the human preference. And this is also why you when you use ChatGPT, it basically aligns with your intention relatively well most of the times. So for us, some of the interesting directions that we are pursuing can be divided into those following categories, four categories shown here. One is communication, medical communication, and two is resource building, three is practice, and the fourth one is in terms of surveillance, and in particular for pharmacovigilance. And first, let's take a look at the using ChatGPT in medical and scientific writing, the communication part. So in this study, we evaluated the abstracts that are generated by ChatGPT for 50 scientific medical papers, and we gathered the titles and the original abstracts from the current and recent issues of the 5 high-impact journals like JAMA, New England Journal of Medicine, BMJ, Lancet, and Nature Medicine. And then we compared them with the original abstracts. So the prompts fed to the model was please write a scientific abstract for the article with the title and the style of this journal at this link. But note that when we were doing this experiment, the link is superfluous because ChatGPT back then cannot browse the internet, unlike right now. So the ChatGPT that we have used, their cutoff date for the knowledge is around September 2021. And given ChatGPT is sensitive to previous queries in the same chat, we ran each prompt in a new session. So while all the output appears superficially to be formatted as a scientific abstract, we found that only 8, accounting for 16% of them, correctly used the headings particular to the scientific journal in the prompt. And we also compared the reported patient cohort size between the original and the generated abstract. And the patient cohort sizes were a similar order of magnitude between the original and the generated ones. And the Pearson correlation between them in the log scale is has a R value of 0.76, which is pretty high. And you can also see from the visualization here. And so we found that the AI output detector, when we use them to try to see which ones are generated by AI or not, they found a high probability of the AI generated output in many of the generated abstracts, compared with very low probability of the labeling for AI in nearly all the original ones. So it's good that the AI output detectors can correctly detect which ones were original, which ones were generated. But we find that 17 and accounting for 34% of the generated abstract received a score below 50% from the AI output detector. And this includes 5 with scores below 1%. So there was only one original abstract that scored above 50% on the AI output detector. And the detector had an area under the receiver operating characteristic curve, AORC curve of 0.94, indicating excellent discrimination between the original and the generated abstracts. And we also evaluated the ChatGPT generated abstract for plagiarism detection using a web crawling plagiarism detection tool. And nearly all the generated texts seem to be completely original by the plagiarism checker. And so it's consistent with what we have expected, that these texts were relatively original in terms of its generation is not directly copied from somewhere else. But then something more interesting that we did is that we used blind human reviewers to try to identify the ChatGPT generated abstract. And this time, as you can see from the confusion matrix, and reviewers seems to be having more difficulty than those AI-based tools. And that begs the question of what will actually happen if humans cannot really detect whether it's human or real original or generated, but machines can. And then so are we gonna policing ourselves with machines, right? So, and as we found deeper into the results, reviewers indicated that it was surprisingly difficult to differentiate between the two. And the abstracts they saw were generated by ChatGPT was superficial and vague in general and focused on details of the original abstract, such as the inclusion of the clinical trial registration numbers and alternate spelling of words. And they noted that while interacting with the model with use of generated numbers, this including the clinical trial numbers, some of those are incorrect. This is some of the cues that they use to identify the the abstract was generated by the machine. But beyond that, ChatGPT actually writes believable scientific abstract and sometimes with completely generated data or synthetic data. And then these are original without any plagiarism detected, but they are often identifiable using an AI output detector. And sometimes the skeptical human reviewers can also detect it, but not always. And this has profound implications in terms of the scientific review and in general the medical communication process because um, this affects the practice to maintain the rigorous scientific standards. And we suggest the inclusion of the AI output detectors in the editorial process, and then clear disclosures if this technology, like the ChatGPT or some other like larger language models, were used when the papers were written. And we're glad that most of the recommendations, I think, is becoming the mainstream nowadays. And but then there is still the question of the boundaries between ethical and acceptable use of the large language models to help scientific writing. It remains to be determined. So next, let's switch gear to BERT. Remember the GPT-based model is one directional and the BERT model is bidirectional in terms of the attention. And let's also look at a different task, building a knowledge graph resource and um, applications to the biomedical field. Um, and in this case, we were using GPT to try to enhance the interoperability. Um, when we talk about interoperability, besides common data models, there's also the technique of FIRE that can be used to enhance the interoperability by exchanging information between different academic and medical centers. FIRE stands for Fast Healthcare Interoperable Resource, and it's uh, crafted by the HL7 Standards Committee, and it's meant to facilitate uh, effective exchange of the information when different institutions converted their information into the file resource so that basically they're speaking the common language. Imagine that you have people whose native languages are Spanish or English and Portuguese, etc. And then you ask them to all speak English. That's basically what FIRE facilitated health information exchange looks like. And so I've already covered what is FIRE and then the entity that is behind it. I'm going to give an example of what a FIRE resource looks like. So in this slides, you have the FIRE resource about a real-world patient and then the test results of a hemoglobin. And then it's categorized as an observation. And then, of course, you have this JSON-like structure that gives the values or reference range, basically different aspects of the observation, and as materialized in the attributes slots of the JSON-like structure. And this is what you can use to exchange information because of this well-defined structure. When you exchange information with another institution, you guys are basically speaking the same language without any confusion. And this has greatly facilitated the interoperability among different institutions, and FIRE is also a technique that is under this recommendation by many government and federal agencies. And so we wanted to tackle the question of converting textual data into file resources. And just to be comprehensive. So you can try to convert the structured data into file resources, then exchange with another institution. You can also try to convert the text clinical notes into file resources and exchange the information. And we sort of tackle the more difficult problems of text to file. And this is what it looks like in terms of converting a sentence and try to map it to a file resource of a medication statement. The sentence it describes the medication and its uh, milligram tablet and its indications and also its frequencies. And as you can see, you can map that into the JSON structure that looks like what we have seen before. And just to reflect on this process that needs to complete such conversion. If you do it a traditional way, then first you need to extract named entities from the sentences and then use relation extraction to classify the relations. What is the form of the medication? What is the route of the medication? And what is the reason of the medication? And then you need to standardize the terminologies because same medical concept can be expressed in different ways with either uh, morphological or sometimes even lexical variations. And you need to have this kind of standardization in order to map them to the same concept. And once you have mapped them into the same concept, you typically need to look up the concept in a knowledge resource like the UMS in this case. And sometimes you also need to do the calculation of correct dosage and frequencies. And last but not least, you need to properly format it into a JSON-like structure as shown in the bottom. So we reflect on this process and think that this could actually be much simpler because if you just think about the input and output, it's basically given a text blob and output another text blob. And it looks like what large language model can achieve, right? So that's exactly what we did. And so we try to use the GPT to um, with instruction prompt tuning to achieve this task. And the data resource that we have used is actually an annotated data resource that is further built upon the N2C2 NLP clinical challenge of the medication recognition. But then we annotate on top of the medication that are identified all those dosage, schedule, reason, form, route, and strengths. And that gives us this rich information of the corpus of clinical notes with annotated medical medications along with their attributes that are defined as file resources. And then we prompted a LLMs to see if it can achieve the task of giving it a discharge summary, whether it can generate first recognize all the medications and then generate all those uh, attributes and form correctly the file resource that are associated with it. And this is basically the process and some of the comparison models that we experimented with. So for the comparison models, we have resorted to state of the art from both academia and the commercial side. And in the academia, the state of the art was NLP to Fire that we actually built in collaboration with the Mayo Clinic. And the commercial state of the art was from Google Natural Health language interface API. And the large language models that we experimented with include GPT and Llama 2 in that time, and was a 70 billion parameter model, and also Falcon, which is a 180 billion parameter model. And so just to give you a more direct feel about what the prompts that we used, so it looks like the prompts on the right, and it's basically a structured prompt and gives examples, give it a template, and then give it clear instructions on what needs to be generated. And it gives the terminology of SNOMED CT codes that is necessary. And so in this case, you can see that it's actually a knowledge graph enhanced LLM because you can enhance it with SNOMED CT, you can enhance it with let's say ICD, or you can enhance it with unified medical language system, right? So that's up to your own choice. But I think that we can be flexible in terms of what kind of knowledge graph you can support to enhance the model. And when it comes to the annotation, and so basically we have annotated a total of over 3,000, actually 3,600 pairs of free text that has the fire medication statement resource transformations. And so I'm not going to delve into the details about all those spectrum of the aspects, but we can directly jump into the comparison part. So when we evaluate the accuracies of the generated file resources and the exact match of the generated file resources versus what we have annotated, and this is what it looks like. And as you can see, across the board for different aspects of the medication statement, GPT-based model achieves the best performance, and then followed by Falcon in general, and then by Llama. And this is interesting because if you look at the parameter size, I think GPT-4 has 1.7 trillion parameters, and followed by Falcon, which has 180 billion parameters, and then followed by Llama 2, 70 billion parameters. So size does matter here. But on the other hand, I think most of the large language model performance actually outperform both the academia and the commercial state of the art that has been developed with much of the human efforts and especially laborious tweaking of the model, whether it's rule-based or sometimes supplying examples to train a deep learning model. So this is something that is quite scalable in terms of prompt instruction tuning in order to re-steer a large language model to achieve something that is really useful in terms of the facilitating interoperable health information exchange across different institutions. Now let's switch gear again and then extend transformer models to assist the clinical practice. And in this case, we'll look at can we extend the transformer models to handle much longer text spans. And recall that the BERT model, the original BERT, and including some of its clinical variants like clinical BERT and BioBERT, they are designed to handle text input up to a maximum length of 512 tokens. And this is rather limited, and especially if you see those medical reports, they can contain thousands or even tens of thousands tokens. So to address this challenge, researchers have developed the long-former and big BERT models, which extends to a maximum of 4,096 tokens by implementing sparse attention mechanisms. And both models have achieved great success in the general domain, but their adaptability to the clinical context remain unclear. So we aim to create two pre-trained language models, clinical long-former and clinical big BERT. And this will be enriched with clinical knowledge through pre-training on large-scale clinical nodes. And in this case, we took all the nodes from the memory data set and to train and improve the performance of the various clinical NLP tasks by developing models that are specifically trained on long and clinical context. So this is the general workflow, and I want to emphasize on the downstream clinical NLP task. And as you can see, we have natural language inference task, name identity recognition task, multiple of them actually. We also have question answering task and text classification. And through those comprehensive evaluation, we clearly showed that our methods perform the best. But I want to take a moment before elaborating on our own results to mention that there is another clinical study after the publication of our paper that uses different LLMs to adjudicate heart failure hospitalization from discharge summaries, and their result is a perfect underwriting of our contribution, and it's absolutely rewarding to see their acknowledgement on Twitter. And so this is something that is really a cherishable moment from our side. And now let's look at the results with the two long text models, clinical long-former and clinical big BERT that we built. They have consistently outperformed the short text models, such as BERT, BioBERT, and clinical BERT across all the four types of clinical NLP tasks. And interestingly, we also observed that even in tasks with shorter sequences, such as language inference task and open question answering, the long sequence models achieved better results. And so we attributed these improvements to the pre-training stages of the clinical long former and clinical big bird, because where those models can learn more long-term dependencies by extending the sequence length limit. And this allows them to learn a richer contextualized representation of clinical concepts and perform better in various clinical NLP tasks downstream. And so here is the Hugging Face and GitHub links of the clinical big bird and long former that we have built, and please feel free to give it a try and then tell us what you think. So finally, I want to reflect on the potential use of large language models in public health surveillance, such as pharmacovigilance. So pharmacovigilance, its primary objective is to ensure safe and efficient utilization of medications, which involves collection and analysis of safety information. And because the 10,000 participants is typically needed to detect a rare adverse drug reaction during the clinical trial, so post-marketing surveillance is actually necessary to recognize the full spectrum of the drug's safety concerns, because not all the clinical trials, and actually many of them, do not meet that standards of having such a large cohort, right? So, but on the other hand, patient might not report all the adverse drug reactions to their clinicians. In fact, only 1 to 10% of these adverse events is reported to the FDA's official system FAIRS. And in contrary, conversations of adverse drug events, they happen more frequently on social media. And you might guess that ChatGPT also leverages social media data in its training. So we wanted to see whether it can be used to identify the adverse drug event and for pharmacovigilance. Um, so we first evaluated whether ChatGPT can correctly identify the drug abuse from the tweets that were potentially its own training data. And then we then supplied ChatGPT with examples of the drug-related tweets annotated by humans. And in all those 6 cases, ChatGPT was able to differentiate true drug abuse cases from the false ones, establishing the ground for it to conduct more advanced pharmacovigilance tasks. So this is just our sanity check. And we then tested ChatGPT's ability to provide adverse effect information on peak rate, which is approved in 2019. And this is actually before ChatGPT's training cut off the model that we used. So we assume that this information should be properly encoded. This drug is approved to treat metastatic breast cancer, and then FDA also highlighted the urgency for quickly reporting safety issues post-marketing in its approval report. So when we use ChatGPT to try to see the adverse drug event from this drug, the list of the adverse events was comprehensive and relatively accurate. The first 3 bullets from ChatGPT corresponded exactly to the top 3 high sensitivity and high severity adverse drug event observed in the phase 3 clinical trial that actually led to the drug's approval. So this is another sanity check. The other 2 bullets, lung issues and infections, they are also confirmed from FDA and EMA, which is FDA's European counterpart. They're confirmed. Those 2 bullets, they are confirmed in both of their reports. And interestingly, we found that the liver dysfunction, this was not found in the reports we examined, but it could be related to lab measures that were investigated. And so right now, it's hard to determine if ChatGPT fabricated this adverse drug event due to its generative nature, or indeed actually detected some signal from the training source. So this is the signal that is in the lab measures, but not actually mentioned in the report. So it's kind of interesting that ChatGPT was able to pick up on that. And then we try to determine the cause of the ADEs, and this is where ChatGPT fell short. And ChatGPT only provided one drug-specific cause, while the other three, like the individual variability, were highly general. And as you can see in this on this left in this panel of this figure, and then when we ask for scientific evidence to support the only drug-specific cause, the inhibition of the PI3K pathway, this actually led ChatGPT to give mixed results. In two of the papers that ChatGPT mentioned, one of them did not actually contain the word insulin at all, despite the ChatGPT claimed so. For the other paper, the biological mechanisms of how the drug can cause hypoglycemia were discussed, and ChatGPT provided only a close summary, not exact. It says the drug inhibits PI3K, which is correct, but it does not impair insulin signaling as was suggested by ChatGPT. So here you see exactly where it starts to fall short. But nonetheless, I think ChatGPT's reply provided a valid starting point for downstream research, and especially if you have human in the loop to implement some of the safety guardrails to catch those shortfalls and then further improve on that. And with the extensive training data, so I think ChatGPT has the potential to be a pharmacovigilance knowledge database, but it will likely not be a comprehensive one, and in many cases can also be subjective to hallucination issues, as you just see. ChatGPT can recognize for example, furosemide, which has been widely prescribed to treat the fluid retention, along with its brand name Lasix and its Chinese name. But when one of the furosemide Chinese brand names were used, ChatGPT actually confused it with the herbal compound drug. And when its IUPAC name was used, ChatGPT confused it with an antibiotic. And for both cases, a human search on Google yielded the correct results. So this illustrates another dimension where ChatGPT can fall short. Foreign language and also formal language that is not typical English that ChatGPT was primarily trained on. So in addition, the um, the selective coverage of ChatGPT can also be considered for scientific research. So in a task to find the drug-drug interactions, we found that ChatGPT neglected one of the only three DDIs on the drug label, but included two other ones that had low clinical concerns. And these results showed that ChatGPT's limitation in terms of the selection bias and this is kind of for selective coverage can be problematic, especially for domain if you wanted to behave like a domain-specific knowledge database. So we found that a more realistic case is perhaps to leverage ChatGPT's text summarization capability for case review. And traditional pharmacovigilance is conducted by case reviews, which is laborious and costly, time-consuming, and especially due to the unstructured nature of the reports. ChatGPT could help automate this process. And in experiments, we supplied ChatGPT with a de-identified case from the 2018 NTC2 Average Drug Event Challenge. And within seconds, ChatGPT summarized the key medications and the potential adverse drug events that caused these findings with high accuracy. And this is the task that you give it medical clinical notes and then ask it to detect what are the adverse drug event that was mentioned in the clinical notes. In this case, I think ChatGPT can do a quite good summarization job. And this task actually demonstrated ChatGPT's ability to conduct named entity recognition as well as relation extraction. So if you really think about the process, those are probably the two major steps that needs to be done in order to generate this adverse drug event detection signal. So for future directions, let's reflect on what we covered so far. We have explored large language model in terms of the communications of the medical knowledge. We have looked at it in terms of the clinical decision support. and we have looked at its use in terms of the pharmacovigilance, and we have also used it to try to build interoperable resource and tools that can enable the exchange of the health information from different institutions, and especially when augment that with a knowledge graph. Looking forward, one thing I think that is important is to disseminate and democratize this kind of knowledge and resource and tools that we build. And this is a major issue that we frequently encounter in our hospitals and health systems because physicians, they lack the bandwidth and expertise to do NLP or not even mention large language models. So what we have been doing at the health system is what we call bulk NLP. That is to standardize the processing and then bulk process all the clinical notes so that we can map them from unstructured text and extract the structured information, whether it's an advanced drug event, whether it is the patient phenotype, or whether it is the file resource that you need to enable interoperable information exchange. We can extract them with the standardized and generalized or scalable process. And we can either deposit structured information into combinatorial models or frame that into a file resource so that the researchers can query and then use that to exchange with other institutions. And we have built these infrastructures to disseminate these tools, and then all the researchers in our health system can use them in a really self-service manner. And this helps disseminate and democratize those toolings and resource, and they can offer great synergy with the downstream innovation and education initiatives. And look at LLMs itself, and we have identified some of the pitfalls for LLMs, and in particular, even for some of the basic NLP tasks, it demonstrates both good and bad behaviors. So perhaps when you're looking at the part of speech tagging and the name identity recognition, it's good, but then when it comes to relation extraction and also to parse out the structure of the sentence syntactically and semantically, it starts to show its limit and fall short. And so I think there is the urgent need in terms of better augment the logical models so that it can really understand the relations that whether it's syntactically or semantically that are expressed in the sentence or in the text. But on the other hand, we found that LLMs can be potentially used to integrate multimodal health data. Because if you think about it, when we as humans look at structured data, numerical measurements, clinical notes, omics data, imaging data, we often form impressions in our minds and then synthesize all those impressions and reasoning about them. But then if you think about what is the impressions that we have and how do we use, what do we exactly use to reason about things, they are all language, right? So language is the common vehicles for the representation of different data modalities. And then suddenly you have these large language models that are pretty good in terms of mapping those language into representations. So you can imagine that you can use LLMs as common vehicle for integrating the different source of the data and learn a unified representation. And the last direction that is very near and dear to my heart is that we can actually try to think of LLM as the vehicle to help us move from reactive to proactive machine learning. And if you look at traditional machine learning, those are really reactive in terms of responsive to human experts' tasks and data, and then they're tweaking of the models. But this is not sufficient. And people started to realize it. And then they started to sort of making it more proactive. The first level of the proactiveness, I think, is in terms of abandoning feature engineering and getting to the architecture engineering so that the features can be automatically learned. So this kind of feedback loop is already down. But I argue that a bigger feedback loop in terms of recognizing where the data has its weakness or biggest uncertainties, and then guide people to target your data collection, to augment your current data, this feedback loop and through continuous monitoring and the evaluation, this is urgently needed. And luckily, I think dialogue LLMs such as ChatGPT fits perfectly in this proactive machine learning paradigm because it can summarize all this data in a human presentable way, understandable way, and then it can also tackle different human commands in terms of where you would identify more of the either biases or the missing data or some of the biggest uncertainties. It can cater to the human needs. So such a dialogue LLMs can sort of act as an agent when you wanted to achieve this proactive machine learning paradigm. So with that, I want to thank everyone for your rapt attention and close with this message. Let us work together, and it's an open invitation. And I hope we can work together to bring the research and its application to a whole new level. Thank you.
Thank you very much, Professor Luo. We can, if you have time, let's open it up for questions. You can either type your question in the chat and I'll read it, or you can go ahead and unmute yourself and ask Professor Luo directly.